Can you hear me?
Yes, sir.
Okay, we can start. So last time I shared a couple of problems for us to try for practice. So we'll continue the same, and I've also added a few more problems to the list. So uh, okay. So these are all problems taken from various Olympiads, mostly RMO past papers, but I'm also adding some papers from other countries. So USA, British Maths Olympiad, Canada Maths Olympiad, they also have good problems. So we can take some material from there also. And I try to arrange them roughly in the increasing order of difficulty for us. I also try to ensure that this is all of these can be done using the topics which we already know. So we don't need anything extra from what we already know. Okay. So question 3 is the one which we already tried and completed last time. So I'll encourage you to continue trying the next problems. Question 1 and 2 also you can try, but I think question 1 should be simple for everybody to do because very similar question was asked in the practice the practice test which we all do. So question 1 and 2 also you can try if you want, but mainly I'm going to discuss question 4 onwards. Okay. So I'll give you some time to think. Has anybody already found a solution for question 4 and question 5?
Yes,
Yes,
sir.
sir. Yes, sir.
Okay. So then I won't give too much time, but maybe just 5 minutes in case somebody has not tried. So I'll discuss question 4 and 5. Okay. Meanwhile, you can, if you have already tried question 4 and 5, you can try question 6. And you can continue from there.
Sir, can you show the problems for a minute?
Yes.
Thank you, sir.
Okay, so maybe we can discuss question 5. Uh, so that there is no integer a such that 289 divides a square minus 3a minus 19. So for those who have already done the problem, can you give some idea of how to get started?
Yes, sir. So we can, if k is any integer, we can let a square minus 3a minus 19 is equal to 289k. And then we arrange it and use the quadratic formula.
Okay.
And under the square root, we get square root of 85 plus 1156k. So it should be a odd perfect square.
Okay, just a minute. Let me share my. Okay, so can you repeat what you said?
Yes, sir. So a square minus 3a minus 19 is equal to 289k.
Okay.
And we rearrange to get in the form ax square plus bx plus c is
Right.
equal to 0.
Okay.
So we get 3 plus minus square root of 85 plus 1156k
Okay.
upon 2. So here for integer solution, 85 plus 1156k should be
Yes.
odd perfect square.
Yes. Okay.
So from this we can observe that we can take 17 common. So
Okay.
17 into 5 plus 68k.
Okay.
So now for it to be a perfect square, there should be a factor of 7 in the uh, uh, in 5 plus 68k, but it is congruent to 5 mod 7 mod 17. So no
Yes.
solution.
Oh, so this is congruent to 5 mod 17. So
Yes, sir.
therefore, yes. So this cannot be an odd perfect square. That is correct.
Yes, sir.
In fact, it cannot be a perfect square at all.
Yes.
Okay. Yeah, I mean, in a way, although we are using something which we have not covered, but we all know that the fact that if there is a perfect square, then prime factorization always occurs in pairs. So if there is one factor of 17, there has to be one more factor of 17 inside the bracket. But yeah, apart from that, I think everything is clear. Okay. Does everybody follow this solution?
So I didn't get how we how we like prove the last part. How do we say from that?
So because a is an integer, so this formula itself has to become an integer, and that can only happen if the thing under the square root is a perfect square, right? So 85 plus 156k has to be something maybe b square, okay? And now if we split this, this is 17 times this bracket, 68k plus 5 is equal to b square. So clearly you see 17 is there on the right, so 17 has to divide b, correct? So b will, let's say b is 17 times b1. So LHS will become 17 square, 17 into 17 into B1 square is equal to this whole thing. So one a factor of 17 will get cancelled, and you will be left with still 117 on the LHS, right? 17 B1 square equal to 68k plus 5. Now if you just look at this equation modulo 17, then the LHS is divisible by 17, common to 0. This part is also common to 0 mod 17, but this is 5, which is not possible.
Okay, sir, I got it.
Yeah, I think this is a perfectly valid solution. Any alternative approach?
Sir, I did by two methods.
Okay.
In one of them, I just used brute force method, taking modulo 17. I got that if there's such a exists, then a is congruent to 8 mod 17. Then I checked uh, checked a such that a is congruent to 8 mod 17 and such for that for 289.
Okay.
But that was very long. The other one was quite short.
Okay.
That I just constructed one. I just took it as that 19 as 70 minus 51,
Okay.
and so I got it a minus 10 times a plus like a square minus 3a minus 19
Okay.
is equal to a minus 10 times a plus 7 plus 51.
Right.
And then 17 will divide both the factors, and eventually I got that 289 divides 51, which is a contradiction.
Wait. Can you repeat? How do you split this polynomial?
Okay, a minus 10 times a plus 7 plus 51.
A minus 10 times a plus 7 plus 51. Okay.
So if 289 divides this, then 17 divides this. So 17 divides a minus 10 times a plus 7.
Okay.
So 17 is a prime number. So 17 divides either of one of those, but they
Right.
both are congruent to both are congruent to each other mod 17. So 17 divides both of them.
Okay.
And so 289 divides both of them. So 289 divides a minus 10 times a plus 7 and
Right.
also that plus 51. So 289 divides 51, which is contradiction.
Yeah. Okay. Got it. So I'm not sure if everybody followed that, but basically this original polynomial is equal to this expression, and we know 17 divides this whole expression. Out of that, 17 obviously divides 51. So 17 divides the product of these two. But if you notice, the difference between them is exactly 17. So if 17 divides one of the brackets, it has to divide the other one also. So in all, 17 square will also divide this product. And so then if we know that 17 square divides the whole fraction and this part, and therefore 17 square has to divide the remainder, which is 51 also, which is the contract. Okay. I hope everybody followed this method also. And is there any other method? Okay, so I have a method kind of similar to this, but I mean here I think the how to split this polynomial into these two brackets. Somebody may say, how do you think of this idea? But there is a simpler idea which is easier to think about. So first thing is always, I mean, if you ask me what is the strategy in any problem like this, it is divide and conquer. So if you are given a large number as a divisor like 289, and if that number is a prime number, then it is harder to do anything. But because here we know it is 17 square, so we can do this thing one at a time. So we are given 289 divide this expression. So first start with the what this implies, that if 289 divide this, then obviously 17 divide this. So now reducing everything modulo 17, I mean minus 19 can be just replaced by minus 2, right? So this is the same as 17 divides a square minus 3a minus 2. And you see how to factorize this now? So this is simply a minus. This can be factorized, right? Or it cannot be. Oh, I think I made a mistake of assuming that this can be factorized. No, that cannot be wrong. But so at this point, there is two options. I think what you said, you can do that you can brute force and find out which value of A will satisfy this equation. So I think that will narrow down the list of possibilities. Or
Sir, we get that a is congruent to 10 mod 17.
okay, so basically, if you write down the whole table of, I mean, all possible remainders of A, so A going from 0, 1, 2, 3, etc. And for each case, you write down what is the remainder of this modulo 17. So you will find that, so you are saying that 10 is the one which satisfies this equation. Okay, but let me just think if this can be factorized in some other way. I mean, basically the thing is you have the freedom to adjust any of the coefficients by plus minus 17. So by some clever adjustment, if you can convert this into a polynomial which can be factorized, then that is one way of thinking about solving this problem. So I mean, by hindsight, I know if you are talking about that A is common to 10 mod 17 is a solution, then I am considering converting this to basically A square minus 20A. And basically A square minus 20A plus 100 will be divisible. So, I mean, so this is equivalent to this modulo 17, right? And this is nothing but A minus 10 whole square. But of course, the problem is how do you know this in advance, that how much you have to adjust each factor is not known as such. So sometimes you may run into difficulties like that. Or maybe the other adjustment I'm thinking is you can add 17 instead. So you can convert this also into a square plus 49a, sorry, plus 14a plus 49. So this will lead to a plus 7 square. So in either case, what you get is 17 divides a minus 10 or 17 divides a plus 7. Okay. So there are multiple methods to arrive at. See, if you're not, I mean, it's quite possible that it's hard to think of any such clever adjustment. So then the brute force approach is always there. You list out all the possible remainders and see which row is giving you a remainder of 0. So that is always possible. So one way or the other, you arrive at the first conclusion that what is the remainder of dividing a by 17. Okay. So now suppose you have got that the remainder has to be 10. So which means a is of the form 17k plus 10 for some k, right? Once you have this, you can substitute this back in the original equation. So what you originally had a square minus 3a minus 19. Now, I mean, originally it was 17 square divided this. Okay, but if this value of a is correct, this remainder 10 is correct, and substitute this, then what you should get is one factor of 17 should come out common from the RHS, right? So if you substitute and check that, what do you get? So a square minus 3a minus 19 is 17 square k square plus okay. So out of this, if we look at, I mean, we combine all the coefficients as per their degree. So 17 square k square. I mean, this part we can actually ignore because we are dividing everything by 17 square, but I will just return it. So the coefficient of P is 289. So I mean, nicely, this is also divisible by 289. This is also divisible by 289. But I'm illustrating a general method here that what could happen in general is so something is wrong there.
Sir, that minus 57 should be minus 30.
Minus 30. Oh, I think I accidentally multiplied 19 by 3. Yeah, this is the right one, right? So this should be 51. Okay, so see, you are getting basically 289 or 17 square divides this whole thing. So I mean, again, here you can quickly jump to the conclusion and say that 17 square divides 51, which is a contradiction. But I mean, in some general case, may not happen that way. So if you continue to simplify it one more step, like cancel one copy of 17, what will be left is 17 divides 17k square plus 17k plus 3. So you see how started from 289 divides something to now 17 divides something. So you reduce the divisor by one step. And I mean, in a more complex problem, you have to do this step multiple times. Okay, so this kind of divide and conquer strategy is something that you should keep in mind. Okay? So I mean, divide and conquer basically. And you can do a similar thing in some other problems also. So, for example, if you go back to the linear congruences that we were doing last time, I mean, we had asked questions like find a number such that, let's say, a congruent to 2 mod 3, a congruent to 4 mod 7. Suppose you had some 3 such congruences to be solved. So here also you can do this kind of divide and conquer strategy in the sense from the first equation you can say that a is of the form 3k plus 2 for some k. Now you substitute this into the second equation and things like that. So you can take out divisors one at a time to solve even linear congruences. So yeah, this is a much more general approach which can be used in multiple cases. Okay, so we have seen many different solutions, and you should take away something to learn from every solution. So I think the first one in some way was very direct in the sense that the quadratic equation directly gives you the contradiction here. Second and third solution also, which Arno explained, both of them are valid. So what was the second solution, Arno? I forgot. So this was the one which were factorized a minus 10 and a plus 17. But what was the other solution?
Brute force.
Okay, brute force. And then this is the third solution, divide and conquer. Okay, so I mean, keep in mind all of these different techniques because you don't know which one will be applicable in which problem. Okay. Then, so that was question 4. Do you want me to discuss question 1 and 2? I think if I give you time, you should be able to do it on your own. So I'll skip question 1 and 2. Is that fine? So then question 5 we can discuss. Actually, give me 5 minutes to work out question 5. So just as a hint for those who are trying question 5 and not got it yet. So the greatest integer function, how it works, just to illustrate that, that will give you some idea about how to approach this problem. So the greatest integer function, as I explained last time, is the largest integer which is smaller than or equal to x. Okay, so for example, greatest integer of 3.14 is 3, and the greatest integer of a negative value will also be rounded down. And of course, the greatest integer of an integer does not change. So the important thing is that for any real number, okay, so if x is any real number, right? If you consider what its greatest integer is, it will always be smaller than or equal to the number itself. And that number is basically trapped between the greatest integer and the integer after that. So this is the most important, you can say, inequality which defines what the greatest integer is actually. It's the integer which traps that real number between its. So it's a semi-open interval, this one, okay, in which that integer is always quantum. So pretty much this is the only thing that you need to know. Everything else can be derived from this. So I mean, keep that in mind, that you have to use this idea somehow whenever you are trying any problem which has greatest integer in it. And I mean, there's one more related notation which is called the fractional part. So that is denoted by curly brackets. So curly brackets is nothing but this difference. Okay, so whichever is the leftover fractional part from the greatest integer to that number. So that part is denoted as curly bracket. So both of them satisfy basically the same identity. So this is what you have to use somehow. Okay. So how do we get started
Can you
with
give
this
2
problem?
minutes and I'm very close. You just have to calculate.
You want more time?
He suggests 2 minutes.
Okay, sure. So meanwhile, just to give you a hint, first thing you have to do in a problem like this is observe some patterns from smaller numbers. So I expect everybody should try and create a table of small values of A1, A1, A2, A3, and see what is the pattern. So you can make some conjecture that what may be happening. So if I make a table of N and AN over here, so the AN is defined as. So note that there are two greatest integer functions here, N upon greatest integer of that. So in fact, you can do it if you want one at a time. So N, the greatest integer of root n, and then N. So that will help us to understand what's happening. So first thing you'll notice that the square root of n itself, when does the greatest integer of the square root of n change? Only at perfect square, right? Okay. And in fact, it could be helpful to look at the ratio also, n upon greatest integer of square root of n. This is 1 upon 1.
So is the answer 45?
I don't know the numerical answer.
I think the answer is 43.
Yes, sir, I'm getting 43.
I think you might have missed some edge cases.
Okay, sir.
Sir, for root 7, is it 7 over 3?
No. 7 or 2, right? I mean, square root of n is square root of 7 is 2 point something.
Okay.
You always round down, right? Okay. But if you create this kind of table, do you see the pattern that and our condition is we want to find all n such that an is greater than an plus 1, which means that the sequence decreases from the first term to the next term. So in this pattern, if you see where the decrease is happening, it is happening here and it is happening here. So I mean, you can make a conjecture that seems to be happening at all the perfect square boundaries, right? So I mean, based on this, you can make the claim that an is less than n plus 1 if and only if n plus 1 is a perfect square. Okay, can you see that we can make this conjecture from the data? But of course, we have to prove it that why will this happen?
Yes,
So-
I got the answer is 43.
Yeah, okay. So I mean, there are two things to be checked here. Right? First is whenever you have if and only if, you have to prove that at the perfect square this decrease will happen, and conversely anywhere in between the value will not decrease. So you have to prove both the things, right? So how will you start to prove these things? So claim. So there are two parts. Part one is that if
Can I tell?
yeah, sure. So which part do you want to do first?
Sir, I've done both the parts. I think the easier one is that if n plus 1 is not a perfect square, then an plus 1 is greater than or equal to an.
Yes, sir. Because I think the denominator doesn't change in that case.
Yes,
Right?
then the denominator is constant, and
Yes,
so
sir.
n plus 1.
Yeah. So the value can remain the same or decrease, but it will not increase ever. Is that the idea?
Yes, the fraction itself is greater, so the greatest integer will also be
Yes.
greater.
Yes, correct. So so first part is that if n plus 1 is not a perfect square, then I mean n plus 1 can be equal or decrease, increase, but can never decrease. Somebody else, Adya, do you have any solution?
Sir, I wanted to tell if n plus 1 is a perfect square.
Okay, sure. So I'll come for that. So I think this part, if n plus 1 is not a perfect square, one way to characterize this, so the fact that n plus 1 is not a perfect square, how do you put this mathematically? So you can say that it is trapped between two perfect squares. So if you look at consider a range of numbers, k square plus 1,
Sir,
k square plus 2. Yes.
so if n plus 1 is not a perfect square, then an plus 1 will always be greater than an, right?
It can be equal, right? Because the
Yes,
thing
it
is,
can be
see,
equal.
this fraction, if you see, it is increasing, but the greatest integer of this fraction is an. So, I mean, if you take the greatest integer of 3 and 3.5, they will be equal,
Okay, sir.
right?
Sir, if an plus 1 is not a perfect square, then we can divide it into n by floor of square root of n plus 1 plus
Hmm.
1 by floor of square root of n plus 1. And here the 1 by floor of square root of n plus 1 is less than 1. So we can eliminate that. And we get that n by floor of square root of n should be always greater than n by floor of square root of n plus 1, which is not
Uh,
true.
yeah, Robert, just a minute. I hope you are not doing the mistake of splitting the greatest integer, because it's not true that greatest integer of a plus b is greatest integer of a plus c greatest integer of b. This may not be true.
No, sir.
That you're not doing that, right? Can you just repeat what are the steps you are saying?
Yes, sir. So uh, n plus 1 upon floor of square root of n plus 1, the whole floor.
Mm-hmm.
So we can divide this into whole floor of n by floor of square root of n plus 1
Okay.
plus 1 by floor of square root of n plus 1.
Yes. Okay. This is fine.
And here 1 by floor of square root of n plus 1 is less than 1. So
Okay.
so we can eliminate that term, and by the condition we get that n by floor of square root of n should be always greater than floor of n by floor of square root of n plus 1.
Yeah. So this is safe to say that this will be greater than floor of square root of n plus 1.
Yes, sir.
This is, I mean, for that, it doesn't matter whether this is smaller than 1 or greater than 1, as long as it is positive, right? The fact that it is positive, we can eliminate that. Because
Yes,
as
sir.
Arnav pointed out, basically all we are using is that if some two real numbers are such that x is less than y, then greatest integer will always be like this. So greatest integer cannot increase if the numbers are decreasing. So that is all we need to use.
Sir, and for this we
And
get
so
that.
this is equal to this, right? Because basically this is going to be equal to this.
Yes, sir. So we can eliminate that case, and n plus 1 is a perfect square.
Sorry, this is the case where n plus 1 is not a perfect square, right?
Yes, sir. So
Yeah,
n plus 1 will always be a perfect square.
no, that last statement I didn't understand. So here we are proving the fact that if n plus 1 is not a perfect square, then n plus 1 will be greater than or equal to n, which we have proved here. So from there, what are you saying? Therefore, n plus 1 is a perfect square.
Yes, sir. Sir, we assume that n plus 1 is not a perfect square. So I'm getting that floor of square root of n should always be greater than floor of square root of n plus 1, which is not true.
Oh, so I think we are doing the converse with that. So we want to show that at the perfect square boundary, the n plus 1 will decrease. That is the part we are doing. Okay.
Yes, sir.
Okay, got it. Okay, but see, does everybody follow how the forward part works? That if you assume n plus 1 is not a perfect square, then these calculations can be done. And the most important step is this one, where you can replace square root of n plus 1 whole floor by square root of n floor. That does not change the value of the fraction, because it is between the boundaries of the perfect. So, I mean, if you want to illustrate this in a mathematical way, one more way of doing is that consider the series of numbers k square plus 1, k square plus 2 up to the next perfect square. So, when we say that n plus 1 is not a perfect square, which means that n plus 1 has to lie somewhere in this range, right? So, you can make the claim, and in exam you can do this directly. Okay, you can claim that there exists a k such that k square is less than n or strictly less than n plus 1 and strictly less than k plus 1 square. So if n plus 1 is not a perfect square, it has to be tracked between two other perfect squares. Okay. So if you do it this way, then you can sort of formalize. Now you don't have to write. I mean, basically, every time you write this floor of root n plus 1, you can simply write k in that way, right? It's easier to write everything. But yeah, essentially the argument remains the same. And the important thing is that if k square is less than n plus 1, which means k square is less than or equal to n also. So which means that the floor of square root n is also k. Okay, so these two things together will help us to finish part 1. And so for part 2, Rudra, I think I understood your argument, but let me just think how to express it better. Because I mean, basically we have to be clear what are we assuming and what are we trying to do. So part 1 was showing that if n plus 1 is not a perfect square, then n decreases. Now for part 2, I think you are proceeding by some kind of contradiction. So your claim is that if n plus 1 is a perfect square, then an plus 1 is less than an. And now, I mean, you are saying that if possible, let this not be true. So let an plus 1 be greater than equal to n. And from there, you are showing some contradiction. Is that how you are approaching?
Yes, sir. Yes, sir. Like that.
Okay. Can you do one thing and just write your argument properly and send it to me? I mean, I want to make sure that there is no mistake that you're doing there.
Okay, sir. I will send
Okay,
it.
just send it to me.
Sir, I used a direct method.
Okay, so can you give us some idea how to get started with that?
I just assume that n plus 1 is equal to k square, where for some k belong to natural numbers,
Okay.
and then just found out n and n plus 1.
Okay. So basically, now the picture is that k square is there and k square plus 1, etc. So basically, we have two ranges: the numbers below k square and numbers higher than k square. And so if we directly compute, let's say what is n plus 1. So n plus 1 is nothing but n plus 1 upon square root of n plus 1 whole floor. So you see that this is going to be everything is going to come out nicely because n plus 1 itself is whenever it's a perfect square, this fraction also becomes an integer, right? So this is nothing going to be k. And what about an?
N becomes k plus 1 because then floor of root n is k minus 1. So, and n is k square minus 1, which is k minus 1 times k plus 1.
Okay. So see, because k square is equal to n plus 1, which means so k square is n plus 1, which means n is k square minus 1. So the greatest perfect square below n is now k minus 1, right? So therefore, now this is floor of, so the denominator will now be k minus 1. And the numerator I can, instead of writing n, I can write k square minus 1. So now this is k square minus 1 upon k minus 1, which is simply k plus 1, which is again it's a perfect integer. So the outer greatest integer sign also goes away. And so now clearly here we see that n has to be.
I didn't get the last part.
How we computed an?
Yeah.
Okay. So see, now we are assuming that n plus 1 be a perfect square, k square. Okay. So if n plus 1 is a perfect square, so which means that square root of n plus 1 is k, which is an integer. So
Yeah.
the greatest integer of this is going to be k itself. So when we compute n plus 1 is what? N plus 1 upon this greatest integer. So it is n plus 1 upon square root of n plus 1.
Yeah.
So basically it is k square upon k. If you want, you can write one more step. This is nothing but k square upon k. So that is going to be equal to k. And for n, so n is now one smaller than n plus 1, which means it is just missing the k square. So n is going to be in the range of k minus 1 square up to k minus 1 square plus 1. So k minus 1 square plus 1. This whole interval which ends at k square minus 1. So any number in this range, if you take, right, and n is this, by the way, but any number in this range, if you take square root of n, it will be k minus 1 plus some fractional part, right? So the greatest integer of this is going to be k minus 1. So that is why this fraction became, so the denominator became k minus 1 and numerator, which is n, is k square minus 1. So now this is just, you can factorize and get k plus 1.
Okay, sir, I got it.
And so once you directly computed an plus 1 and an, and so there you see that an plus 1 is in fact smaller than n. Okay,
Okay.
so I mean, once you have proven this claim both ways, that basically this, what was the claim? This, that an is less than n plus 1 if and only if n plus 1 is a perfect square. Now all you have to do is count the number of such n plus 1 in that given thing, 1 to 2000. Okay. So again, before we go to the next problem, just take some time to understand what all did we use here, which are the problem solving techniques that you can take away from this. So first thing is observation. Make this table, observe the data first, make some conjecture. That is the first step. Once you have made the conjecture, understand firstly it's an if and only thing. So you have to prove both parts. And out of that, the first part, when n plus 1 is not a perfect square, is easier to do because there the denominator remains constant. And where n plus 1 is a perfect square, that is also easy actually because you can compute directly. So, I mean, there were some calculations, but nothing that we cannot handle once we have the right strategy. So, are you realizing through these problems what I always said from the beginning, that Olympiad problems are not difficult if you break them down into 3-4 small steps, right? If I give you the same problem as step 1, prove this, step 2, prove that, I think everybody can try and get it. But those middle steps are not there. So, these intermediate steps are what we have to guess. By more and more practice, you will become better at that.
Sir, I have constructed a variation on this problem.
Okay.
So,
Okay.
like just in the final statement, all the previous setup is same. Find all n such that an is not equal to an plus 1, or else like we have just found out the an greater than an plus 1. You can just say find all such that an plus 1 is greater than an.
Okay, okay. So here we found all, first the given problem was all an such that an is decreasing. So now the variation you are saying is let's find all the n where this is happening.
Yes, sir.
Okay. And I mean, once you answer both these questions, the complement will be the cases where n remains constant. So in fact, we have three. We can basically partition the set of natural numbers into these three sets, right? The ones where n decreases, the one where it increases, at one it remains constant. So we can split the data into three such buckets. So looking at the numbers which you already written, so which are the values where, so these are the values where n was decreasing, the perfect squares. Now which are the values where it is increasing? So I see, looks like it's increasing all the time, is it?
No, sir. What we have written is n by floor root of root n.
Oh
We
yes,
have
yes.
to
So I
put the
have to
again floor of that.
okay. So I have to add one more column over here. So the value of an itself is 1, 2, 3, 2, 2, 3, 3, 4, 3, 3. This is a bit more complex. So now here the like places where it is increasing. Interesting. Maybe let's take some time to think about this problem. Others can also think about this, and yeah, if you come with any solutions to this, you can send it on the group. Okay. It's a very interesting series actually. Okay, any other comments about this problem? No. If not, then you can try question 6. Okay, meanwhile, let me add some more problems to this worksheet.
Enlarge the screen a bit.
Sorry?
Okay, yeah, enlarge the screen a bit. Yes.
Okay.
So what is the meaning of eventually becomes constant?
Eventually becomes constant means that there will exist some index k, so that from ak onwards, ak is equal to ak plus 1 equal to ak plus 2, etc. up to infinity. So I'm see again, best way if you just start with some number n and try a few examples, you'll see what happens with the sequence.
Yes.
Eventually, the value of the ak does not change.
Okay.
Firstly, does everybody understand that this ak will be uniquely defined indeed? This goes back to what we had said last time about complete set of residues. So the numbers from 0 to k minus 1 form a complete set of residues modulo k. So exactly one out of those remainders will complete the divisibility by k. So I mean the starting number n is the only one which matters. Once the first a1 is fixed, the entire series is going to be uniquely defined.
Yes, sir. So basically, ak will be a1 plus a2 plus 1 up till ak minus 1 mod k.
Minus of that, right? Because we want the sum to be equal to 0 mod k.
Yeah, okay, right.
So have you taken some small numbers and verified that this is actually happening?
Yes, sir.
Yeah.
Okay, anybody has solved the problem? So what can you say is the effective condition? See, what they've asked us to prove is that the sequence eventually becomes constant, but can we derive something which is easier to prove if you observe how the data is looking? Yes, Gaurav.
Sir, what I thought is that if the series reach, sir, if a of k is equal to k into I, where I is less than k and greater than 0, then the
Mhm.
series will become constant.
Yes, why is that?
So because since I is less than k and it is greater than 0, therefore for k plus 1 I can just add I, and it again means it is again divisible by k plus 1. So that series can go on by adding on i's. Therefore,
Yes,
I will
correct.
be the constant term. So if we can prove that it will eventually reach a point that the a of k is equal to ki, then so
Mhm.
yes, sir.
Yes, correct. So yeah, I think that's the right
Sir, I
observation.
think then I found a solution. I missed this observation, but I think then I
Okay.
found a solution using Kerr's observation.
Okay, okay, that's good. Okay, so see the way the problem is set, what we are the property that is given to us is that a1 plus a2 plus a3 plus up to ak. K always divides the sum of these k numbers. That is what is given to us. I mean, the way I look at it is fundamentally, if you look at how the sequence evolves, let's say we start with a1 is equal to 1, the simplest case. Okay, there you'll see that a2 is also 1, a3 is also 1. So this is the simplest case where all the numbers are 1, 1, 1. Okay, and basically you don't need to start deviating from 1 at all, because any number of ones you take consecutive, obviously their sum will be divisible by k. So, and the same thing will be true if I multiply this whole sequence by some constant c. Okay, c, all of them are c. You'll see that this equation also, this series also satisfies the same condition, because K will divide any number of them. If you take K of K such terms together, that is nothing but C times K. So this is of course going to be true. So once you reach a point where and finally we are adding one term to the end. The terms before that, the numerical value does not matter. All that matters is the sum, right? So if you reach a point where A1 plus A2 plus up to AK, this sum is basically C times K, then your actual values of A1, A2, AK may be different, but from this point onward, it will be treated equivalently as if it were all C K times, right? So do you see that the sequence, even if it's A1, A2, A3, AK, which are all different numbers, or C, all C, which are different numbers, doesn't matter. From this point onwards, both sequences are going to proceed in the same way, right? So in that sense, basically, once you arrive at such a point where this A1 plus A2 plus A3, all of them is equal to CK, and this last term is also equal to C. So once that happens, then that is where we can continue from. So Arnav, you're saying you know how to prove this part, that how basically your claim is that there exists some K such that AK is equal to C times K.
Yes, where C is less than K.
Yeah, where of course C is less.
Yes, sir.
Sorry, AK is equal to
Sir, sum of AK
Yes, summation AK.
in some sense.
yeah, sorry, summation. That A1 plus A2 plus AK is CK, where no, sorry. Can you state your exact name? I'm not sure what.
Yes, sir. There exists K such that A1 plus A2 plus dot AK is equal to K times maybe say C,
Okay.
where C is less than K, less than or equal to K.
Sir, it has to be less than K, right? In this case.
No, but this such a K. For every K, this has to be true, right? What are we doing?
No, sir. Why should be this be true for every K?
Okay. I think what you're adding where C less than K is the part which you're adding. Okay.
Yes, sir.
This sum is going to be a multiple of K, but that quotient could be larger. So what you're
Yes,
saying, there
sir.
exists a K where. Oh, this is the claim. Okay. Let me give some time to think why this claim should be true.
Sir, I think few observations, like for few trials for few small numbers might help us in the observation. I
Okay.
tried doing that.
Okay.
Sir, over here,
Mm-hmm.
sir means just a second, just a second.
Okay.
And the K where it starts is a very nice number which we get by the observations.
Yeah, I think it happens at the nth element, right?
Yes, sir.
Basically.
It starts at the nth element.
Yes.
At the nth element, we get the constant term.
Yeah, I also observed that, but why is that happening? That I'm very curious about. Okay, let me think about this. So A1 is n. So 1 divides A1, 2 divides A1 plus A2, 3 divides A1 plus A2 plus A3. And basically we are claiming that at the nth term, right? Of course, A1 plus A2 plus A3, this is true. But at this point, what also happens curiously is that this sum is nothing but K times, not K times, but some constant times n, where
Yeah, whether that constant
is
is less
one.
than or equal to that number.
I don't know, this come down to some inequality basically, because
Yes,
see,
sir. It's an inequality.
the restriction, see the fact that A1 is given, but A2 belongs to the set 0, 1. A3 belongs to the set 0, 1, 2.
You can just take the maximums of all of that.
Right.
And it's a nice just 1 plus 2 plus 3 plus dot plus n.
Right. Oh, interesting. So see, here in this claim, the basic thing which you have to prove is that obviously this product is going to be C times n, but the important claim is that C is less than n. So that upper limit on this sum is the one which is solving the problem, right? And that upper limit comes from, as we are observing, that the fact that A1, A2, A3 themselves are restricted by these ranges. So therefore, the total sum of all of this will be, so A1 is less than, A1 is equal to n, A2 is less than or equal to 1, A3 is less than or equal to 2, and An is less than or equal to n. So if I add up all of this, the sum A1 plus A2 plus An has to be equal to less than or equal to n plus, oh wait, oh, sorry, 1, this should be n minus 1.
Sir, I didn't really understand why this thing will be established at n itself.
I also didn't
And why not
understand,
at-
but that's the thing. I'm also very surprised by it, but logically it makes sense now. If you checked a few
No, sir,
numbers, that is what happening every time.
I was able to prove that after n, all of them become constant, but I'm not sure if it every time it will happen at exactly the nth step.
But see, what is going to happen now? See, if you add up all of these inequalities which we agree, therefore A1 plus A2 plus An is nothing but n plus n minus 1 plus all the way up to 1, right? This is n into n plus 1 by 2.
Yes, sir.
And
So k will
so,
be less than or equal to n plus 1 by 2.
yeah. So this is nothing but we know that this is some c times n. So therefore, c has to be less than n plus 1 by 2, less than or equal to. So
And
here
that is less than or equal to n.
that is less than equal to n. In fact, I think it will be strictly less than n for most cases. Okay. So therefore such a c exists, but now having established this, now what is the next step? So I think we just have to formalize the argument that we did earlier, right? So having proved that, so therefore this n exists. So therefore A1 plus A2 plus An is a multiple of n where c is less than or equal to n. So now what will happen to n plus 1? You see n plus 1 is equal to c is the only option here.
Yes, sir. So because if we add c, then it
Yes.
becomes n plus 1 times c, which is divisible by n plus 1.
Yeah.
And
And already we know
continue.
that there only such a single value can exist. So therefore an plus a1 plus a2 plus an plus 1. This has to be a multiple of n plus 1, and that can only happen when n plus 1 is equal to c. This will become n plus 1 times c. And I think from here an induction kind of argument should be sufficient, right? By induction, I think we can prove that all the values have to be equal to c.
Sir, what I was trying to prove is that no, sir, since now the solution is complete right here.
Yes, yes.
But according to our observations, this is happening at exactly the nth step, but I'm not sure we have proved that.
Why not?
Sir, we have proved that after the n steps, this sequence is a constant, but you may not know that the constant terms may start before n, before the nth number.
Yes, yes, it could happen before in luck. As I said, if you start with a constant term, what your claim is that it cannot happen before n, or that you don't know.
Yes, sir, I'm not sure about that. By observations, I'm getting that, but
Mhm.
I don't know if that is actually true or not. Like it's not even the solution of this problem, but in
Yes,
general
yes.
for
Yeah, that's a fair point. I think in all the examples I took, it started at exactly n. I've not seen a case where it starts before n.
Yes, sir.
But can we conclusively prove that suppose it starts happening before n, what can go wrong?
So if, for example, for a n minus 1 is equal to some n times c, then c should probably be n minus 1.
If n minus 1 is equal to n times c.
So then
Yeah,
c should be
obviously.
n minus 1, right?
Yes, or some multiple of n minus 1. So yeah, it can be only n minus 1. Yes.
Yes,
I'm
sir.
taking the n as 12, the constant term starts at the fifth term.
N has 12.
Yeah.
Then what is happening?
The constant term starts at the fifth term.
Oh, interesting. So A1 is 12. In fact, yeah, 12 is an interesting number because it's basically all of the first value will be 0, right?
Yeah, till A4 is 0. A5 onwards is 3.
Okay, interesting. A5 is 3, correct? So now here you already have, this is,
yes, sir.
yeah, 5 into 3. So now from here it will always be 3.
Yes, sir. So I think this observation is invalid.
Oh, interesting. So why it happens for 12? Can't it happen for a smaller number like 6 also? What happened for 6? If 4 will.
Sir, even at 6, it starts at 4.
Right. Yeah. Okay, so now this leads to a completely different question. Find the set of all natural numbers for which this sequence starts before n. Find all n. Does that? We have to give it some notation maybe that what is the term at which this constant sequence starts? Does that 80 is equal to 80 plus 1 is equal to 2 plus 2 for some t which is smaller than. Yeah, this could be an open problem. I think, I mean, here particularly 12 and 6 look like good candidate because they have so many factors, right? Therefore, these initial zeros are somehow helping. That's what I can guess. But yeah, I think this may be quite an open problem for us to crack. Okay, any other observations about this problem? Okay, this was question 6. So you can try question
Sir.
7. Yes, go ahead.
Sir, I think for composite numbers, this should be true, sir.
Oh, all composite numbers?
So, as far as I checked, most of them are working. I'm not sure for all. Just check.
Okay, okay. Maybe just take a number like 15, let's say. 1. Oh. Right. No, sorry. So I have to keep track of the sum till now. Until the sum is 20, A6 has to be 4.
I tried for 8, it works for 8.
Yeah,
It
I
was means
see
what?
it's working for 15
So it
also.
is working for 15 as well. It is coming before.
Yes, sir.
Yeah. Okay. That's
So I think the
interesting.
composite numbers, there is some special about them.
So because earlier when we tried it on 1 and 2 and maybe 3 as well. So and
Yeah.
all of these are prime numbers, and that's
Yeah,
why
yeah.
I guess that is the
Yes,
thing.
sir.
Yeah,
Actually,
and coincidentally, I had only tried for prime numbers 5 and.
sir, I tried only for 1, 2, and 3. That's why I got that observation.
Actually, even for 5, if you notice what's happening, right? I mean, A1 is 5, A2 is 1, A3 is 0, A4 is 2, A5 is 2. I mean, it starts at A4 actually, not A5. So in a way, for 5 also it's happening before, just one step before n, but it is happening. Yeah, I don't know then. Maybe this is quite a large set actually. Maybe then the complement set may be easier to find. Find all n such that it does not start happening before the nth term. That could be the question. Okay, but anyway, I mean these are all open-ended things to try. So I hope you give it some thought and see. I mean, take it as far as you can. Make the question as far as you can make it harder until you cannot solve. Until then, keep adding something. Okay, because this is a very useful exercise because it helps you to discover what are the limits of each problem solving tool. That inequality helped us to find this answer, but maybe now we'll require something more powerful, and then after that something more powerful. So that's a very good exercise. Okay, question 7. And actually, I just copied question 7, but from the looks of it, may not be too difficult.
Can you give some hint?
Sorry, can you get the answer?
No, sir. I'm saying, can you give some hint?
Hint. Actually, we have done a very similar problem in the practice test, if you remember. The question was, see, whenever you have two polynomials which of a different degree, right? N plus 2008 divides n square plus 2008. You have to always try to see how to get rid of this square term. If this can think of some way of getting rid of this n square and converting back into a linear form, like n times something plus
Squaring
something.
n plus 2008 maybe.
Sorry, what did you say?
By n.
Maybe we
plus
can
2000.
you can square to n plus 2008
Yeah,
and
correct,
subtract.
exactly. That's the idea. So find a multiple of n plus 2008, which you can conveniently subtract from this and get rid of n square.
Sir, I think this is quite simple I got right now.
Yeah, exactly. So once you find out which multiple of n plus 2008 you have to consider, then it becomes a one liner, right?
Yes, sir.
See, looking at this n square, you will be tempted to raise this whole thing to its perfect square. So n square plus 2008, that whole thing. But that's not
Can't we just
required.
multiply by n?
Yeah, you just multiply by n, right?
Yes, sir.
If you multiply this by
Yeah.
n, the n
And
square
n
will
and
go away.
n minus 1 are co-prime, that will help us.
Yeah, exactly. So see, n, we are given n plus 2008 divides n square plus 2008. So we just have to find some multiple of this, which you can subtract from this. So as you correctly pointed out, we can just multiply this by n. So n square plus 2008, n is a multiple of this one. So subtracting, we simply get n plus 2008 divides 2008 times n minus 1.
Yeah.
Okay. And
So
the
then can we see that n plus 2008 times k is equal to 2008 times n minus 1, and then n is equal to 2008 times n minus 1 minus 2.
after this, what do we do?
So we can take the 2008 k to the other side maybe.
Okay. So n k is equal to 2008 n minus k minus 1. Something like this.
Yeah.
Okay. Then what do we do?
Sir, actually, I'm not able to get rid of that k.
Hmm. No, so I have a different approach here. I don't know if this is what you are thinking about, but see, we have to keep doing this. We got rid of the n square and we got a linear term, right? Why don't we get rid of the n also completely from the RHS? Can you see how to do that? Do you understand what I mean? So let me rewrite this as n plus 2008 divides 2008 n minus 2008. Just as we got rid of n square, what can I do to get rid of this term also?
Multiply by 2008.
Yeah, exactly. So n plus 2008 divides 2008 n plus 2008 square, right? So I can subtract one more time.
Yeah, n plus 2008 divides
So
2008
2008 times 2007.
2007. Yeah.
No, not 7, so 9, right? I have to subtract.
Yeah, right.
And from the other condition, you will get n plus 2009 divides 2009, 20,009.
Times 2010.
Yeah, exactly. And now that these are just constant, so you can just list down the factors, and now I don't have to write n plus 2008 every time. Let me just substitute this equal to m. Okay, so this is m and this is m plus 1. So once I find m, from that I can find n. So the question is now reduced to find m such that m divides 2008 into 2009 and m plus 1 divides 2009 to 2010.
Sir, I have a much shorter approach.
Okay,
Sir.
tell us. I mean, is it the same up to any point, or it's
No,
different
sir.
from?
Sir, it is different.
Okay, tell me.
Sir, so n plus 2008 divides n square plus 2008, and now we know that if a divides b, then a divides b minus a, the linear combination.
Yes.
Sir, so n plus 2008 divide n square minus n.
Yes.
Similarly, n plus 2009 divide n square minus n.
Yes.
So n plus 2008 into n plus 2009 divide n square minus n.
Oh, yes, correct.
Sir, and by Euclid algorithm, n plus 2008 and n plus 2009 GCD is 1.
Yes, that is why you can do this, by the way. I mean, I think we have not proved this theorem formally, but if A divides C and B divides C and GCD of AB is 1, then AB divides C.
Yes, sir. So n plus 2008 into n plus 2009 is maybe greater than n square minus n. So n is equal to 1 is only the solution.
Yeah. All right. This is a very fast solution. So see, once this number is much larger than this number, then I mean the only multiples you can consider are I mean either it is n square minus 1 is 0 is one possibility, or n square minus 1 is equal to this number. But that also may not, because we are looking at natural numbers, right? So therefore,
How
this
did
is
you
also,
get that the LHS is larger?
this is, if you multiply this out, the whole thing is going to be n square plus something, right? So it is definitely going to be larger than n square minus n.
Yes, sir.
So finally, the answer is n is equal to 1, is it?
N equal to 1.
N is equal to 1 is the only solution. That is surprising, because see, this one, if you ask me this question, find the m such that this is true. I would think there are multiple solutions possible. Is it not? I mean, because all of these, this is not a prime number, this is not a prime number. So some factorization could have led to a solution. But apparently not. Okay, maybe once we actually start to factorize and look at the factors, maybe there is nothing in common. Yeah. Okay, but did everybody follow this solution? That from the given condition, we just subtracted one copy of n plus 2008 to directly get this expression, these two. And then the fact that the GCD of the divisors is 1 allows us to combine. By the way, I think it's a good exercise to prove this theorem, that why is this theorem true in the first place? That if A divides C, B divides C, then why can we combine AB this way if the GCD is 1? So leave that as an exercise for you to try. But assuming that theorem, and you can safely assume this in RMS, there is no difficulty in that. So then you can directly get this.
So,
Yes.
so I didn't get why n square minus n should be equal to 0.
See, once this is true, so if we write it formally, what are we saying here now? N square minus n is a multiple of the LHS, right? So n square minus 1 will be some k times n plus 2008, n plus 2009. Okay. Now, if you compare the magnitudes of the LHS and RHS. Basically, we have one more result, which is that if A divides B, then the modulus of A has to be less than or equal to modulus of B, right? So in that spirit, what we are saying is the modulus of the divisor, this n plus 2008 to 2009, that is such a big number, right? The modulus of this whole thing has to be less than or equal to the modulus of n square minus n. And we can get rid of the modulus sign because everything is positive. So n plus 2008 into n plus 2009, this whole thing has to be less than or equal to n square minus n. So I'm writing this left hand side, this big number as some capital M. So we are looking at multiples of capital M, such that, and I mean, obviously the reverse inequality is also true. This is also going to be less than n plus 2008 into n plus 2009. Because if you expand this, we are going to get n square plus lots of positive terms. So clearly, this whole thing is going to be greater than n square minus n.
Yes, sir.
So the only way is so actually, yeah, I think my claim was wrong. I didn't n square minus n is equal to 0 was one possibility, but the other possibility is just equality. So yeah, maybe I mean the right way to say is that if A divides B, either B is 0 or if B is non-zero, then mod is less than mod. So therefore, there are two cases to consider. Either, so case 1 will be n square minus 1 is equal to 0, or case 2 will be n square minus 1 is equal to the whole divisor. But I think that will not lead to any solutions. So therefore,
Sir, could we scroll up a bit?
And it won't give any solution because then LHS is negative and RHS is positive.
n square minus 1 is not negative, right? But
We cancel the n square and then
yes, correct. Yeah, and clearly LHS is much smaller than RHS.
sir, and n plus it's n plus 2008 times n plus 2009. So when after we cancel the n square, we get RHS is positive, LHS is negative.
Yeah. Okay, so case 2 will not lead to any solution. Case 1 leads to the only solution, n is equal to 1.
Sir,
Yes.
we had come to a point,
Mhm.
sir, where n divides, say, n plus 2008 divides 2008 into n minus 1. So could you go on that step, sir? So after that, I didn't quite get it.
This one or some
Yes, sir.
Okay. So which step you want me to explain? You got this, that we are from here we are subtracting a copy of the divisors. So we get n plus 2008 divided n square minus n. And similarly from the other equation we can get n plus 2009 divided n square minus n. And because the divisors have a GCD of 1, therefore we can say that the product together will divide n square minus n. Is this part clear?
Yes, sir.
Okay. So here, I mean, you can ignore the calculations. The first observation is that the divisor is so big and the RHS is so small. So that can only happen if the RHS is either 0. So that was the case which gives us the solution. Or if not, the RHS has to be greater than the LHS. And that leads to contradiction. So that is all we are doing here.
Okay, sir.
Okay, does everybody follow? Why? I mean, basically, why does this step solve the problem for us? That whenever a big number dividing a smaller number, that is where that should lead you to some solution. Okay, so I mean, what is an important idea in this problem and some other problems also? There is a topic. I mean, it's not a topic, but a problem-solving technique called estimation. Okay, estimation and bounds. These are very important concepts, particularly for Olympiad kind of problem, because what it helps us to do is constrain the number of trial and error you have to do. So you always look for opportunities to estimate how big a number can be, try to put limits on that, and then that will help to solve the problem. So you can just imagine in your mind that when LHS becomes very big, I mean, what grows faster, the LHS or the RHS, something like that. But I'm curious to know, I mean, of course, this is a nice solution, but can we complete this solution also? So earlier what we had done was we found that n plus 2008 divides this 2008 into 2009. So this m, find the value of m such that both of these are true. I mean, it should be possible to complete this also actually. I mean, at this point, because as I said, the RHS are finite numbers, so you can just list down the factors and see if such an m exists. But that could be cumbersome if the prime factorization is quite big. So we will continue to give it some thought that can you complete this solution also in some way. Obviously, now here m is equal to 2009 is a solution, right? And that is coming from n is equal to 1. So this is obviously a solution, but why is this the only solution? That is what I don't know.
So,
Yes.
so sir, over here we have m and m plus 1, and they divide 2008 into 2009, and m plus 1 divides 2009 into 2010. So out
Yes.
of these two numbers, we have to find like two consecutive multiples. Like,
Yes.
so I guess in that case, we have 2009 and 2010. But
Mhm.
then when we multiply it by 2, or we just find a bigger number, we won't get consecutive. So I think that is why it will be only one solution.
Yeah, but that is still, I mean, can we formalize that observation in some way that where we can definitely say that such a number will not exist? That's what I'm looking at. Okay, but anyway, we can give it some thought. Maybe there is some way to complete this solution. Yeah, it would be interesting to know. If you get some solution, you can just send it on WhatsApp. Everybody can take it. Okay. But if there are no other comments on this problem, then we can go to the next one, the last one, question 8.
Sir, does the first statement say that the let capital N belongs to natural numbers?
Yes, that should be capital. Yeah, just make that correction. Or you can make the second one as small. Basically, they are the same natural number.
I got some method.
So maybe just give some time.
Sir, is the answer like the natural numbers? Like the answer is n, the natural number or natural number?
It will be dependent on n, right? Small n.
Yeah. So like, is it like only the natural numbers? Because I'm getting something like that.
I mean, you want to find the number of solutions, so the answer will be a natural number.
No, I mean the solutions are 1, 2,
Oh.
3, 4 like that.
Acha, I don't know actually.
Okay, sir.
Do you observe that? Yeah, I mean, I don't know if x is a natural number, but x has to be a rational number. Can you see that?
So I'm intuitively feeling that x will only be with a set of integers, because what I'm feeling is that if say n is the fractional part of the
Take it as 8 because n is already a variable.
sorry.
No, what are you saying?
So what I'm intuitively feeling is that it's only the set of integers, because in the RHS we are squaring a very small quantity. Like if
Yes.
squaring a quantity which is less than one, and in
Yes.
the LHS we are not doing that. And in LHS I think we are first increasing the gap and then reducing. Well, RHS we are first reducing and then again squaring it. So I'm intuitively feeling that it's only the set of integers, but I'm not sure.
See, the difficulty is when you do x square, right? You don't know necessarily whether you're increasing the gap or not. I mean, the gap between x and fractional part of the integer part of x, and the gap between x square and the fractional part of x square, could be cases where it's actually reversing. So I mean, yeah, the first observation is correct that both LHS and RHS are trapped in the range 0 to 1. But why, if the x square crosses a boundary of an integer, then it can circle around and become smaller, right?
So I tried to take the fractional part of something and I found a equation that says like let it be 8, then
Okay.
a square plus 2a times floor function of x is equal to a square. So 2a floor function of x is equal to 0. So either
Yes.
floor of x is equal to 0 or a is equal to 0. But floor of x can't be 0 because it's like bound from 1 to n. Therefore a has to be 0.
Oh, wait. Maybe. Can you repeat your calculation?
So shall I say from the start?
Yes.
Yes, sir. So first I took the fractional part of x as a, and
Okay.
I got that. So x is equal to integer part of integer part, that is floor function of x plus a the whole square, that is floor function of x whole square plus a square plus 2a.
Wait. No. Wait. This hold on. So x is fractional part, integer part of x plus a. So therefore, x square is, you are saying x square is this thing whole square, correct? Or
Yeah.
what is your claim? Yeah. Okay. So then this will be integer part of x square plus 2 integer part of x a plus a square. Okay. Then.
So then yeah, I simplified it, and then the next that we get, it is equal to a plus integer part of x whole square, like that.
No, that's
Yes,
what. No, I'm confused. What is the starting point which you are assuming?
That
What?
will be a square. Sorry, yeah, that will be a square.
No, let me write it from the beginning. So this is what we know, or rather, what we have to solve: x minus 30 integer of x whole square. Now we have assumed that let this be true. So I mean, how are you using the given equation is not what I'm understanding. How are you using this equation?
Yeah, so the second, the RHS, it is x minus floor function of x. That will be a.
This is a, so this is a square. Okay, correct.
Yeah, so that will be a square. The whole square will be a square. And
Yes.
then what we have got is floor function x
Oh,
square
okay, yes.
plus
Okay.
2x.
Yeah, so now I see. So from this equation, I mean, I can rearrange this and say that x square minus. No, but that is the problem, right? Okay. I mean, what does this equation give me? X square minus floor of x whole square is equal to 2x a plus a square. And see, here we have x square minus floor function of x whole square, and here we have x square minus the square and the floor function outside. So we cannot equate these two, right? I don't know if that's what you're doing.
For the LHS, it will come down to a square plus 2a floor function of x, right?
LHS of which step?
The last equation that is written.
Okay, so what will this come down to?
We'll get a square plus 2a floor function x.
Okay, let me try that. Yeah, I mean, basically what I've written here. So that these two are equal.
Yeah.
So, but I'm still, we are not using this anywhere, right? The given equation, how is that getting used here?
But no, that is a square, so we can just put it.
No, that's the mistake which I am pointing out. So, see the given equation, what is this term? X square greatest integer of the x square, where here it is greatest integer of x whole square. These may not be equal, right? Not necessarily. Okay.
Sir, can you give just 1 minute? I think I'm close to something.
Yeah, sure.
Sir, I have an argument. Sir, so we know that the RHS is nothing but the fractional part of x the whole square.
Yes.
And sir, if we simplify the LHS part of it, so yes, sir. So what I was because so it's basically x square plus floor of x square.
X square plus floor,
minus,
not
I'm sorry, yes, sir.
minus floor of x square, correct?
Yes, sir.
So it's the fractional part
So-
of x square basically, right?
Yes, sir. So minus,
Yeah.
so minus floor of x square or minus floor of x the whole square? I would like to just learn.
It is minus floor of x square. So it's not the whole square.
Yes, sir, yes, sir. So yes, I have considered that itself.
Yes.
So if I were to represent x as, sir, if I were to represent x as floor of x plus fractional part of x and then square it.
Okay.
So in the floor of x square, the fractional
will-
part of x square will be negligible, so it won't count. And the remaining part, what I'm left with is floor of x for the whole square plus 2 into floor of x into fractional part of x.
Yes.
So if 2 into floor of x into
Now if I take the floor of both sides, so floor of x square, we can ignore this term because it's an integer. So we'll be left with floor of this whole thing, right? X fractional part of x square plus 2 integer of x.
So we can ignore that part, the fractional part. So that will
But-
always come out.
No, not necessarily. Sometimes it can exceed, right? I mean, if we are very close, let's say this term is very close to the boundary of an integer, and this is just the term required to push it across the boundary, the value can change.
Okay, so just saying, I'll just check.
I mean, maybe, if what you're saying is to, we have to at least prove it rigorously. Just intuitively, we cannot be sure about that.
Sir, what I am getting is that 0 is equal to, let's say, something capital M minus floor function of M plus A square, and that capital M is floor x to the whole square plus 2 floor x A.
This is a solution you're saying?
No, sir, I'm stuck here.
Okay. Okay, so I mean, before maybe we won't be able to complete the proof here, but just one quick observation. Does everybody see that x has to be rational? Did you come to that conclusion? Or if not, then at least let me explain how I came to that conclusion. Then we can see how we can take it forward. So this is what we have, starting from the very given equation. So this is what we have. So if I just expand the RHS as it is, sorry, 2 times x into integer part of x plus integer part of x whole square. So this is what we are saying. Out of this x square will cancel, and so we'll be left with, and taking everything to one side. So I can write this as 2 times x times integer x is equal to x whole square minus integer of x.
So
use now if I divide everything by integer of x, so 2x is equal to greatest integer of x minus x square upon. So do you see this has to be RHS has to be a rational number, which means that x is a rational number. Is that fine?
Sir, won't that be plus in the second step that we have written? Plus floor root of x square.
It should be plus x square. Somebody was saying something?
yes, sir. So fractional part of x the whole square will always be less than 1, right?
Yes, it will be less than 1.
Yes, sir. So therefore, floor of fractional part of x square will always be 0, right?
No. Why are you getting to that conclusion?
So because floor is yes, sir. So because fractional part of x the whole square.
Wait, let me write. Fractional part of x, the whole square, will be, I mean, it's just a fractional part, right? So it will be stuck between 0 and 1.
Yes, sir. So therefore, its floor will always be 0, right?
Its floor is, yeah, the floor of this is 0, that is correct. But that is, I don't know where we are getting that kind of term. So I don't know how that will
So
help
over
us.
here in that particular part when I was trying to
Okay,
floor
here.
of x square.
Mm-hmm.
Sir,
But
so over here when sir, so its value sir, so this part can be ignored, right?
No. So that's the thing. See, if you add two numbers which are both very close to integers, I mean, basically 0.9 and 0.8, the sum of these two, you cannot ignore any of these terms. I mean, because just the floor of this is 0 and floor of this is also 0, but together the sum, the floor is 1, right? So how can you say which part you can ignore. You cannot ignore any part.
Okay, sir.
Okay, so we can see, most important thing is observe what is the question asking. It is not asking you to find all x. Find the number of solutions of the equation. So this is what you can do, and see, x is going to go from 1 to n. So we all understand that this. I don't know what is this one. Observe how, let's say you start with x equal to 1 and just plot the graphs of LHS and RHS. That is the hint I would like to give. So plot LHS and RHS graph. Okay. Plot how x minus, so this is the RHS, as x travels from 1 to n. See, we all know that integers it is going to be 0, right? So basically the graph is going to look like something like this. It always starts from 0. It will never reach 1. So maybe we have to draw a closed dot here and open dot here. So it will be always like this for the RHS, and similarly you get a graph for LHS. And wherever these two graphs cross, those are the solutions we are interested in. So just count how many such crossings are there. If you count that, then that is the answer we are looking for, right? Okay, so that is the hint for you. I'll leave it at that, so I'll give you some time to think. But in general, I mean, we have solved some questions today. Of course, we cannot do too many questions because we also have to cover some theory. So we have not started with prime numbers, etc. But you see, just the whatever you know so far can also be used in so many versatile ways. So we have to keep practicing that. I would say the most prominent sources are of course RMO papers, but you can look at other national contests also. So Canada Olympiad, British Maths Olympiad, USA, all of those have good problem sources. Okay, so you can keep trying and keep improving your problem solving skills in that way.
Sir, what was that BMO?
BMO is British Maths Olympiad.
Okay, sir. Okay.
Sir, in this last question 8, I'm getting that there is no solution of x in 1 to n, range 1 to n.
No, but integers will be solutions, right?
Yes.
All integers will be, apart from integers, there are no solutions. That is what you're saying?
Yes, sir.
Oh, interesting.
Sir, we can also show that by if we take some root value, then it won't.
But the thing is, x can be any rational number or any real number. So it doesn't necessarily have to be a square root of something. It can be some odd number like pi or e also. So I mean, we have to try to solve the most general case.
Okay.
Okay. But anyway, yeah, we don't have time for puzzle today, and also I have not thought about anything. So yeah, that's all for today. So next time I will continue. We'll just finish this problem, but then we'll get back to the theory of prime numbers and some other congruences.
Sir, what we did right now, the calculations for x belongs to rational numbers. Those calculations are reversible also, right?
Those are reversible, but what do you mean by reversible?
If and only if.
Yeah, they are if and only. That is correct.
Then maybe we can try to prove that the RHS. I'm not sure what we are trying to prove.
Yeah, even if that's if and only if, I don't know that how that helps. But I think the biggest hint was given by Advait just now, that I mean, as he says that at integers, obviously we know we have solutions. Now, as it turns out, like if you draw the graph of LHS and RHS and you count that there can be at most n solutions, and we have exactly n solutions at the integers, then we are done, right? So that is the hint. Okay, but anyway,
Sir, by algebraic manipulation, I forced that fractional part of x has to be 0, and so all in.
Oh, interesting. Maybe if you have written your solution, can you just send it on WhatsApp?
Yes, sir. Sir,
Okay.
on group or personally?
You can send it on the group. That is fine. Okay, thanks.
Thank you, sir. Bye, sir.
Bye. Thank you.
Sir.